Hello everyone, this is Vidushi Singh Chauhan. I'm having my roll number 227044. I'm here to present the topic of advanced algebra. My topic is splitting field. So here we will read out about splitting field. Let fx be any polynomial of degree x greater than 1. That means we have to take any polynomial, that is fx, of which the degree, that is x, should be greater than or equals to 1, or a field f. Then a field extension E of f is called splitting field or decomposition field of fx. If, first point, fx can be factored into n linear factors of E. Okay, and यानी कि what we are saying, that means कि fx should be factored into n linear factors over E, and then there doesn't exist any proper subfield E dash of E containing f such that fx can be factored into n linear factors over E dash. That is, f is a subgroup of E dash belongs to E, that is E equals to E dash. Here f is called the base field or the initial field. यानी यहाँ पे हम क्या कहेंगे, f को क्या कहेंगे, then in this condition we will call f as base field or initial field. In other words, we say that E is a splitting field of fx. Then in this case we will say that E is a splitting field of fx if E contains roots of fx and E equals to f a1, a2, a2 to an. The field generated by f and n roots a1, a2 to an of fx in E. So now we will read out some examples of a splitting field. So let us consider that fx equals to x minus under root 2 and x plus under root 2. So equals to x square plus 2x 2, that is x belongs to qx. So the solution is, this is not the splitting field extension over qx. q2 is a splitting field for x square minus 2 belongs to qx. यानी अगर हम q2 के रखेंगे तो ये क्या कहते हैं, x स्क्वायर माइनस 2 जो है ये qx में बिलोंग करेगा. दैट मीन्स एफ एक्स क्यू माइनस एक्स स्क्वायर माइनस 2 विल बिलोंग्स टू qx. Rx. Then R is splitting field extension over R. Q under root 3 under root 2, where W is the omega is the cube root of unity. That means omega equals to e की power 2 pi by 3. Here this is omega, that means cube root of unity. Q under root 2 is a splitting field over x square minus 2 belongs to qx. C is a splitting field for x square plus 1 belong to Rx. And we have another example, question number 2. That means find the degree of the minimal splitting field of x की power 6 plus 1 over q. Let us take fx equals to x की power 6 plus 1. Roots of fx equals to 0. That means when we have to find the root, we will put the value of fx equals to 0. That means if we find out the root, then these will be the roots. So I have not presented here the roots, but I think you guys can find it out. So the roots will be I under root 3 plus minus I and this Sridharacharya formulas. So okay, these are the roots. So take a k as minimal splitting field of fx over q. Then q is here, kq equals to q under root comma I, that is q under root comma I, q under root 3, q under root 3 comma q 2 ये, then q 2 bracket बाहर आ जाएगा, and then q minus under root 3 and then q. Now under root 3 satisfy the minimal polynomial x square minus 3, and q is degree of 2. So also plus minus I satisfy polynomial x square plus 1 over a degree q, that is q k comma q इक्वल्स टू 2 ब्रैकेट में 2, यानी कि जब 2 की पावर 2 रखेंगे देन इक्वल्स टू 4 हो जाएगा, 2 इंटू 2. नाउ वी विल रीड आउट अबाउट algebraically closed field. A field K is said to be algebraically closed field if every non-constant polynomial fx which has coefficient in K has 0 root in K where fx belongs to Kx. In other words, a field f is said to be algebraically closed if every polynomial in fx of degree greater than 1 or greater than or equal to 1 has a root in f. Example, given that fx equals to x square minus 2 belongs to qx, fx does not equals to 0, that means that it gives q equals to under root 2 as root of fx. Q is not algebraically closed in under root q. So there is another theorem on algebraically closed field, that is, if K be an algebraically closed field and f is an algebraic extension of K, then f equals to K. Conversely, we can say that if K is a field extension, then K is algebraically closed. Okay, that means if K is algebraically closed field, then f is an algebraic extension of K, and then fx equals to K. So in this case the f will be equals to K. And then conversely we can also say that if K is a field, that means we consider K as a field, then the extension K is algebraically closed. Okay, so this will the theorem. And now we will read about root of a polynomial. So what is the root of polynomial? Let E be an extension field of field f. Any element A belongs to E, that means there is any element which is belonging in E, is called root of polynomial fx, that is belongs to f gray x if f equals to 0. Root field, let f is an algebraic extension of field K and let E be an algebraically K to E is extendable to a monomorphism form f to E. Properties, if K is a field, then following statements are equivalent. K is algebraically closed. Every reducible polynomial is Kx is of degree 1. Every non-constant polynomial in Kx is split in Kx.